Hello everyone, July 24th, Saturday. Now let's do this. Word ladder. I think I've done word ladder before. Oh yeah, I think this is exactly the same thing I did before, I think. This was in a question of the Amazon interview. Microsoft? I don't remember. This is one of the things I remember that we tried and we didn't get it. I'm curious. I'm just gonna go check if this is the one I've done before. It's a hard question for sure. But now I'm gonna look at a solution. I'm just gonna check if I've done this before. Oh no, I've not done this before. I've probably done word ladder 1. Let's see, let me just search. Word ladder. I think I have, yeah, I've done word ladder. I've done that. That one was for one of the interviews. I forgot which one. All right, we're gonna do word ladder 2. Do I remember how to do word ladder itself? I don't remember. I think, Lord, I think it's a very smart solution. Because you have to jump. That's what I remember, you have to jump. Maybe it's union find. Anyway, alright, let's take a look. A transformation sequence from word begin to end using a dictionary word list is a sequence of words such that every adjacent pair of words differs by a single letter. I think I was trying to solve this using a try and it didn't work. Every SI for I is this is in word list. Note that begin word does not need to be in word list. SK equals N word. So everything here is inside a word list, but the begin word doesn't have to be. Giving two words, a begin and an end, and a dictionary of words, return all the shortest. Oh Lord, I have to return all the shortest transformation sequences from begin to end, or an empty list if no such sequence exists. Each sequence should be returned as a list of words. So hit and cog, we have hot dot, hit hot dot dog cog, hit hot lot log cog. Okay. Hit and cog, we cannot do it. Cog is not in a word list, so we cannot do it. All right, so the beginning words, the length is 5. End word equals beginning word, which means every word is the same length. We have 1,000 words. Words I, everybody has same length, yeah. Begin, end, and a word list I consists of lowercase. Begin is not equal to end. All the words in word list are unique. All right. I remember. It's a graph. It's a graph. We build a graph. And then we basically we're going to DFS the graph. Well, we are talking about shortest path, so it's not DFS. It's going to be BFS if we want to go shortest path. Let's take a look. So let's create a graph out of this. So we have hot. Hot gonna go to dot, right? And dog no. Hot can go to lot. Log is no. Cog is no. All right. So the dot. Dot can go to dog. So dot go to dog. Dot can go to lot. Dot cannot go to log. No cog. Dog. Dog no. Yes and yes. So dog can go to log and go to cog. Lot can go to log. Lot can go to log. But it cannot go to cog. Log can go to cog. Log can go to cog. Okay, so now we have this. Let me write it even better. So actually, we can start. I'm also going to include hit in it, right? Hit. So hit can go to hot and hit. That's it. Hit can only go to hot. So hit, we have a start, and we have actually an end node. End node is cog. All right. So actually, let me rewrite this. So I hit, go to hot, go to dot, and a lot can go to each other, and this one can go to dog. Right? Dog can go to log. Log and lot together, and both dog and log go to cog. All right. So we have a graph, and all we need to do is to traverse it so that we can end up in cog. So we go hit, right? And hit can go to hot. Hot we can go dog, a dot dog log, a dot dog cog, or lot log cog. Yeah. Is it? I mean, BFS. No, we want to short it. So BFS. So hit, go to this, and hot we can go to dot or lot. But if we push it in already, so we don't push it again. So we pushing dot, pushing lot, right? And then when we pop dot out, so we can see what we can go with dot. Hot we went already. Lot is inside the queue, so we don't do it. So we can only push in dog, right? And now from lot we can only push in log, right? And then from dog we can only go to cog. Then we have it, right? We have it. But how do we trace it back? That's the question, all right? We have to trace it back. So every step we have to keep track on the path. How do we do that in a BFS situation? Interesting. In a BFS situation, as Google? Yeah, sounds like it. So a BFS, we're gonna start, right? And then the first node, we push it in. How do we know which path we are on? Dios míos. How do we know which path we are on? I mean, I can traverse the entire thing, but if I traverse the entire thing, if I go like DFS, then I don't know if it's the shortest. So it has to be BFS, right? It has to be BFS. If it's BFS, then how do I record? So I have something, right? And then I have a bunch of children. And I pick a children out. When I pick the children, I need to know where I come from. So when I go for each children, I need to pass in a list, a new list. For every time we have to pass in a new list, right? When I visit a current node, then my parent passed me a list of paths that lead to me, and then I will add myself to the path, and then pass this new path to the next one. Okay, that is reasonable, and it's not too big, it's not too long, because the total length is 1,000, so at most this path is 1,000 in size. And do we copy? We have to do copy for each path. For each children will have its own path. Therefore, we have to copy when we pass it on to the next. And fortunately, I think in Python, when you pass a list in the actually, no, I don't think there's no backtracking in this case. It has to be a copy. So everybody has to be a copy. And once we hit, right? Once we hit the cog, once we hit the end, the first time we hit the end, that is the shortest path. So like from dog, I go to cog, right? And then, but from log, I'm not going to cog. That is a problem. That is a big problem, because the way that we're doing it is if something is inside, then we don't. Yeah, if something that's already inside the queue, then we do not revisit it. However, we should revisit, like when we reach dog, right? And dog will look at the children of dog. Dog has dot, has log, right? And then both dot and log has been pushed into the queue, so we don't do it. So we will push cog into it. And so cog is in the queue. Now when we pop a log out, and log, it will look at its children. It has lot, dog, they both have been visited before, and cog has been visited before as well. But if cog has been visited before, well, we should visit again, because that's just the second path, all right? And then when cog passing out, and we process it, we get the actual path, and then we stop right there. We stop at the end word. That is a good solution. I think it might work. All right, let's give it a shot. So first of all, we need to create the graph. How do you want to create a graph? Well, the graph will be a dictionary. So we're gonna use actually, we don't need to use a deck, but we do need to use, I like to use a default dict for this. So I'm going to say default dict. The other things doesn't really concern us. Okay. So we're going to do a graph. So a graph will be a default dict. Oh no, default dict with a list. All right. How do we create it? Ooh, how do we create it? Good question. Very good question. How do we create it? I mean, is there any faster way to check? I can just zip them. Okay, zip them. So length is 5, it's fine. So we're gonna say 4, right? For I in range, len. I think we can use. Can we use product? just trying to be fancy. I think from iter-tools, right? iter-tools import product, right? And we say A is 1, 2, 3. B is 4, 5, 6. Right. Product. I have the list product. 2 iterables, right? A and B. Let's say A and B product. We have 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, and 3, 4, 3, 5, 3, 6. That's exactly what we want. Exactly what we want. So we're going to do from iter-tools import product, and then in here, no. So in here, what we're going to do is for A and B. That doesn't really matter. It doesn't mean anything. A and B in product, word list and word list. All right, and then we say if A and B they only mismatch by 1. How do we express this mismatch by 1? If mismatch by 1, we can zip them. So we're going to zip A and B, and we say A equals B, right? And then we're going to sum now A equals to B. So we just say letter A equals letter B for letter A, letter B in zip, and when we sum this, if they equals 1, which means having 1 difference, then we're going to say graph A dot append B and graph B dot append A. Right? So this is how we create the graph. Let's go step by step. All right, I want to make sure that every step is correct. So let's use this as an example. Hit, all right, cog, CFG, and we have a word, a list. This thing. Nothing fancy, right? Nothing really fancy. We're just going to check, see if the logic is right in, I did something wrong. Yeah, there we go. And this will be here, and the answer is this. Well, we can sort the answer. That's fine. It's not in my concern right now. All right, and then last thing to change. Okay, so that's the first test case. Let's just do one test case for now. So begin word, and word list, and answer, sorting, blah, 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 and then we say if sorted result equals sorted answer, and do this. So what we want is print graph. Just want to see. Has no, of course I haven't changed it. Find letters. Oh, this is also wrong. Begin and word list. Then type is not iterable. Let's just return this. There we go. So hot, I just checked on my hot. Need to go to dog lot. Oh, that is not correct. That is not correct at all. Huh. Hold on. I think this one might not be right. What's a zip? Letter A, letter B, or letter A, letter B, in zip, say dog, and cog. Yeah, that's right. Or say if it's equal to. Oh, if it's not equal to. If it's not equal to, then we get a false. So if I want to reverse it, so it's going to be not this. Alright? So which means if it's not equal to, we record a 1. No. That is not right. Let's try this. No. What did I do wrong? Hold on. I don't understand. Let's print. Let's print letter A, letter B for now. Yeah, that's good. So if we say equal, equal, I think I know. They're all false, true, false. How are they all false, true, false? Shouldn't be false, true, true. Oh, because it's equal to 1. All right, let's change it. Let's say if it's not equal. Yeah, if it's not equal. Yep, that looks better. Yes, it's not equal. There we go. So we say if it's not equal, then but we have repeats. Why do we have repeats? Hot, go for dot, and hot for lot. And when we go dot, A and B, hot dot, right? Hot dot, hot lot, and dot, a lot and hot. Isn't it supposed to be the product should be only once, right? I'm very confused on how to use the product. I thought it's only happening once. Alright, let's comment out all this and just to see. Hot, hot, hot dot. Right. Oh, dot goes back to hot. Ah, trying to be fancy. Didn't work. Alright, let's go the stupid way then. For I in range, land word list. For J in range, because I don't want to like compare and check. I mean we can. What do you say? No, I say no. I say I plus 1 to land word list, make it clear what we're trying to do, and we'll just say a b equals word list I and word list j. And then if this, right, we do this, have to print, and then we get a graph. Yep, there we go. That's what we're looking for. Dot has 3, lot has 3, dog has 3, log has 3. Yep, everything's good. Actually, we need to also put the begin word in it. All right. How do we put the begin word in it? So we go through each word. So we can put a begin word here, right? We say same thing. Huh. All right. Let's use for IA in enumerate word list, right? And for J in this, and go word list J. Letter A. Let's do this word list J. All right, and then here, what we can do is if. Okay, so I'm going to copy the same thing, but just change. Alright, so if letter A is not equal to letter begin, and letter A, letter begin, and zip A and begin word, then we say graph A dot append begin word and graph begin word dot append. Oh, then what if it occurs again? Good point. What if it occurs again? So nope. I don't like it. I don't like it. This is fine. So we get this one done, and then we say if begin word is not in graph, right? Then for A in word list, we say this thing, right? If letter A equal to letter begin, and then letter begin, zip A and begin word, then graph begin word dot append A and graph A dot append begin word. So then we print graph, and we have one more thing. We have hot dot lot, and we have hit as well. And for hot, we have hit as well. So that's the graph. Okay, the graph is good. Graph is good. Then we say if and word not in graph, then return empty, right? We have this situation. All right, then we're gonna do BFS. How do we do BFS? We need a queue. It's going to be this, and we're going to have a res. It's going to be this, and what we're going to do is say q is going to be equal to a tuple. We'll push a tuple in, so it's going to be begin word, right? It's initial, and begin word, right? That's the path. So when they say while q, right, temp is equal to this, and we say for, say node. Actually, we can say for word and path in q, right? For word and path in queue, what are we going to do? Find the children. For child in graph word. Oh, we also need to be having something called visited. This is going to be a set. All right, for child in this, if child not in visited, or child is equal to end word, then we push the child into it. So we say queue, not queue, temp dot append. We're gonna push child and the path plus child into it, right? If the child is visited and it's not the end word, then we don't do anything. So we go blah 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 blah, push everything in, right? So this is for each word and the path, and then we check the children and push the children inside. Go to the next one, blah blah. We exhaust the queue, and then we fill up the temp. And then we're gonna say queue, well, equal to temp. Now we do that again, right? And then we're gonna check here, right? I'm gonna check here if word is equal to end word, right? We're gonna say rest.append path plus end word, and we say we hit it, right? We hit it. So what we're gonna do, we're gonna have a flag. Where is the flag? Well, the flag is going to be the rest, because we're looking for the shortest path. And there might be other paths to the end word. So if we can find the shortest path, and that should be the end, right? That should be the end. But the shortest path should be at the same level. So we have to check all the queues, right? And we append the rest, which means while this and not rest, right? If rest is empty, we keep going, but rest, as long as we have something in the result, we have a path in the result, then we shall break, right? So here we'll have something in the result, and after we do this, we don't continue, or we don't have to do this anymore, so we just continue, go for the next one, because we already reached the end word. So we go back to this, and I pop out another one, we push it in, go back to the front, we exhausted the rest. Actually, you know what? If word is equal to this, we do this, right? And if not rest, then we do this. And that's like if the queue, if we have more things in the queue. So I just want to end it early. That's basically what I want. I just want to end it early. So I think I don't like to be like this. I'll just say if rest, continue. Because in the queue, we're going to have lots of words, and the end word might be pushed multiple times, but it might not be adjacent to each other. So it might be other words in between. So every time it comes out, if the word is the end word, then we get the result, and we continue to check the next one. If the next one come up is not the end word, but because we already have the end word because the rest, right? Then we don't have to go through this. We'll save some time, and we'll keep going. So the whole purpose is to exhaust the queue to find all the end word in it, and once it's done, you can do this. That's fine. Go back up to here, and this one will be false, and then we can return rest. Okay. with all these analysis, this is the time to shine. And we fail. Why do we fail? Because we go 2 cogs. That is interesting to say the least. Because when we pass, okay, so we don't have to do this anymore. So that's just 1. We just go pass. This one we pass, all right? Let's try the next one is hit and cog as well, but the dictionary is different. And they remove the, they just remove the cog. So just copy and paste and remove cog, and this one shall return an empty. Not enough value to unpack. That is very interesting because I have a check. Where does the error happen? Hold on. I think it's here. What? Begin word and word dictionary word list, right? And the result. Did I do something wrong? Oh, I forgot the comma. There we go. Both pass. All right, let's give this one a shot. Let's give this a name. This is a edge case. Edge case. Right. And this one, give a name, BFS. I'm going to give this one a name. This one should be clear enough. We're trying to build a graph. Okay. I'm going to test both. Let's just try it. Pending. Judging. Taking a long time. I think we have a wrong answer probably. Oh! We got it. It's a right answer, but we time out. We timed out. We passed 21 out of 32, but this one times out. Okay, TLE. That's how a difficult question looked like. All right, which part? Lord, that's 1,000, I guess. I'm gonna try how long it's gonna take to run on my laptop. Probably a lot of time. Anyway, so I need to process this thing. All right, so first thing is I'm gonna change everything into single quote and change everything into this, and then copy and paste. Ooh, it's a long thing. And run it. Oh, I didn't have the answer. I do not have the answer because I timed out, so I don't have the answer. Doesn't matter. The answer is I do not know. Oh wow, it does take a long time. Okay, so that's not gonna work. That is not gonna work. Can I cancel it? Which means the graph is too complicated? Is that what it's supposed to be? Man, I'm canceling. Come on, cancel. And check my activity monitor. Yep, it's canceled. All right, let's comment out these and also comment out this. We can do this, but comment out this. And before we go, let's print a graph. I just want to take a look. So the graph is not too bad, 200 something milliseconds, but oh geez, the graph is huge. Graph is huge. Oh! Did you put it in visited? I forgot to put that in visited. I was like, why does it take so long? You put visit. I mentioned it here, but I never put it in. Visited.add child. I forgot to put in visited. Right? So it's not in visited, or this is equal to ant word, and I put in visit. That's fine. It's a set, so we'll just replace it, and then we add it. Then we got it. Right? Then we got it. I'm not sure, but the first two will be correct. So the last one, it depends. I just need to add one more line. That I have the tool, but I forgot to use it. Let's try it. We have it. We should try. Run code. No. Ha! No, I got it wrong. There should be two paths. Don't sweat it. Don't sweat it. Let's take a look, closer look. Again, we're gonna do the same trick. Change all that. Then I'm gonna change all that. Come in here. Oh man, this is long. Even longer. So come on the first two and run it. Fail because we only get one. I get set. Oh wow, there are three. Set caught con an in ins its ito ipu im ism. Yeah, I got the last one. But the first two is missing. That is very interesting. Why? They should be in the same queue, right? Because it's BFS, we start from the beginning word and we just spread out, right? And then if I pick it up, a child, and I pick up my child, I pick my child. It says we go layer by layer. So if we, at a certain point, if I reach, then everybody should reach it as well. Interesting. Why? Path plus child. Visited.add child. If child is not visited, if child has been visited and we don't visit it, and child in graph word, yeah, if child is and, and then I push the child in. So the end, okay, let's just try it. If child is only once, only one time. All right, so what we're trying to do now is we let it run. Let it run. We let it run to the end. Oh, wow, we let it run to the end. It's still not right. That means the problem is not. Hold on. problem is not with the DFS only get 1. Are you saying that my graph is wrong? Hold up. Let's print graph begin word. So the graph begin word is set. We shall be able to go to cot. We have get, right? And what is happening? I have cot. I have cot, we have get. Which is fine. Hey, I don't want to run debugger on this. Word and path. Hey, that's by the dust. Let's see, word and path. So we're gonna get a tremendous amount of data. So word is set, path, that's the beginning, right? So set, we go to cot, yeah, blah 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 to get, and we go to set again. Oh, okay. I forgot about that. Still not right, but we'll prevent that from happening. Okay, so now set cot. I think my answer is cot. Set cot. My question is, what happened to set get? Set get. Set cot yet cat bet met get. Set get key, set get key, and GTE and ATE. Right, so we are ATE. Keep going, cot. Bet and get ATE, ATS. Yes, ATE had go to ATS. And get set cot cat bet get ATS go to ITS. I did not go to ITS. From ATS, I did not go to ITS. Because I do not go to ITS, I do not go to the end. I think I know the problem. Because ITS has been visited already, so ATS can go to ITS. Ah, I see. Jesus. And that's when we end with get. So we only have cot. And get is something else. And cot eventually go to IBM and ISM. Right? And I know. So what happens is the graph goes out and comes back into one path, and that path goes to ism, right? The thing you want, which means some path needs to be repeated, some path needs not to be repeated. All right, think about how you're doing it right now. So what I'm doing right now is from the start, right? From the start, I go through all the paths and I make sure that each node is visited once. So in this case, we have ATS goes to ITS. I mean, look at it here is better. So ITS is the main thing, right? ITS. So we have ATS go to ITS. Let's write it out. So we have ATS goes to ITS, and we have INS goes to ITS, and we have another INS go to ITS. So, oh wow, look at this. Look at this. Set cat can, set caught con, en, and in. So in is another one. So we have ATS, so these two, and we have in is another one. So we have IAN goes to in, and we have ION goes to in. Right? So when we get out of this, we produce one path because we have two convergent events happening. One is the ATS and INS. They all converge to ITS, but because INS goes to ITS first, so when ATS wants to go to ITS, it cannot. But at that moment, ATS doesn't know that ITS actually reached the end. So we just give up right there, right? We give up right there. Which means we need to store the path again. Oh my God. We need to store the path. So what we get, right? What we get at the end is this path, right? This is the path we get. So what we need to do is to go every step back. Like if we have multiple n-word, that means there are multiple non-overlapping paths towards the end. But if the path merges at a certain point at the beginning, so like it's a two paths coming down, but they merge and then they both reach the end, and now we can only get one. But we can backtrack in this one, just go one by one and see if anything, if at any point, right, some other path can reach the same one as here, which means we need to record the path to a certain node. Like we need to record the path to end at ATS, right? Because when we look at ATS, and its children include ITS, but ITS is visited, so we do not keep going ITS in this path. So when that happens, right? When that happens, we need to record ATS and its. What should we record? ATS or record ITS? We should record ITS. Right, that's the children. So we record the children, right? Because this children we cannot keep going, but we have a potential that this children, that its path towards this, right? That thing might still lead to the result, the correct result. So we need to use this as the key to store a path, to store basically this path, right? We store this path with this child, and we get a bunch of this, like bunch, a lot. And as we go through, when we have the end, we're gonna walk back one by one and check if this one has something inside, inside the dictionary. If it's not, we keep going, and then we reach here, then we find, oh, we do have other paths that leads to ITS, right? We have other paths that leads to ITS. Then we get that path, and we append this to the end. So that's another answer. Okay, so we need something more. Something more. All right, I don't like how this was laying out, so I'm gonna change this. So these two are for BFS, and rest is rest, and we need another thing that is the key. So that thing we're gonna call it a potential path. Default dict list. So If child not invisited or child is equal to this, we do this. Else, which means child is invisited, right? Then we say potential path child dot append path, right? We put a path in, so this path includes the parent, but does not include the child, right? So we add that. Now once we're done, we can actually take a look, right? Let's comment out this, and we want to take a look at this potential path, pot path. Oh, we got lots of stuff, but, and let's not look at this. This is not gonna help you, man. So let's just do this. So depending on how many results we have, right? So we're gonna say for path in res, right? So path in res. Oh man, we're gonna append back into the res. I'm not sure if it's, I don't even know if it's legal to do this. I don't think it's legal. There is a way. There is a way. So for I in range, len res. Then because len res is called here, so I can change the size of len of res. I won't affect this. So now we're gonna say for j in range res I, right? It's gonna be len res I minus 1, right? So this is the j. We want to, j is going through each and every one of the word, right? So now we're gonna see if, right, if res I j, which is this thing, that's the child, right? If the child is in, actually we don't have to go to, we can start with -2 because the last one is the n word. We don't really need the n word. So if this one is in pot path, right? If this one is in pot path, then we need to do the pot path, add that, which we can actually make it easier. We're gonna say for pp, or the pot path, in pot paths.get this. If not, going to be empty, right? For this, we're going to say res.append. So these are other paths that leads to the same thing. So res going to be append what? pp plus what? Res I j to the end, right? J to the end is going to be the path. Yeah, so that. What are you doing? What is this? What is this? Result. I got a bunch of things that I don't want. Am I repeating things? Set we have an issue. We have an issue of repeating. We did get, wait, hold on. This doesn't make any sense. This does not make any sense. Because I have set and met. Set, met, what the hell? Hold on. I think the idea is right, but the execution is wrong. Even if I go 1, it's gonna be like this. Yeah, that's not the issue. because everyone here, let's see, print res I and j. So we have IBM, IBO, ITO, ITS, right? And let's print this. Let's take a look. Okay, so I need to unprint both. Just kind of get an idea what happens there. So IBO, from IBO we have, what is this? IBO, IBM, ITO. Huh? Hold up. If child, so potential path is this, right? If child, for child in the graph, right? If child not being visited, or this, then we add this. That's cool. If child is in visited, so which means that's something we visited before, then we add the current path. Else, if the child, hold on. So the child so as we go in, right, and I have multiple places to go to, and I say this one, this is a child, that's a child, and that's a child. So I have multiple child. And now I say, for all the childs, yeah, then I press the path, and the path is actually longer than me. That is not right. That is not right. It shouldn't include me in the path, right? The child shall not exist in the path. So it should be like the next one in the path. Yeah, it should be the next one in the path. How do I do that? Well, you do that by, oh, yeah, how do I know that it's not where I came from? Hold on, let me think. Let me think. So I'm here, right? I'm the current node, and I have a bunch of child, right? So if the child is not where I came from, right? So I came from here, and the child could be this. So it has to be not on the same level, right? It cannot be on the same level, or it's my parent. It can only be my children. How do I code that? I mean, I can, honestly. I just need to create another thing, right? I just need to create another thing that's on the same level, which means it's on the same queue, right? Because I'm going through the queue. Let me think. But for child, I only want the child that's not on the same level, so not my parent. Only that shall work. Otherwise, so it cannot be. It's like here, right? IBO, the path, so the child is here, right? I say the path actually extends beyond. So that's not right. Right? That's not right. That's not right. So for each node, again, a word is a node, and I have a bunch of children, right? A bunch of children. What I want is if the child is the new one, right? Which means child is a new one. All right, where are we? So we have the node, right? And node has multiple children. Why this happened? This happened because I'm probably at ITO, right? I'm at ITO, and I have children. Why would I be on ITO? I'm like somewhere. Maybe. Oh, I am at IBM. I am at IBM, and I have a children. IBO is my children, but that's where I came from, and that should not be. No, that's a no. And also no is, yeah, I think it's going to be convoluted solution. Jeez. So we're going to say Q set. Right? The Q is on the same level. So I don't want the same level. I only want the next one. So Q set equals to set Q, right? So we just say, if not in visited is the overall, right? Elif child not in Q set, right? So, which means it's not in Q set, and the current path -1 is not equal to child. So the child is not my parent, and then I do it. All right, and let's try this. Unhashable type. Oh, it's not going to be the Q. It's just going to be the ay, Dios mío. Let's do temp set. All right, let's do temp set, and at the beginning, we're going to have a Q set. Q set. Q set is the same thing as this. Just one is global, the other is local. And I don't like this anymore. So I'm gonna separate these into different. So these two are both sets. I come in here, rest potential path. So I'm gonna do blah 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 and blah 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 blah, and then visitor.add, right, and the temp set, right, .add child. That's in the same queue, right? It's the next queue, and once we're done, Q set equals to temp set. All right, now going back, now we can say it's not in Q set, and this one we just run it. That's still not right. Child not in Q set, and path -1 is not equal to child. I didn't even feel like change anything. I already said path -1. So path -1, that's equal to IBO. Why would this one still be passed in? All right, we need to stop here and check here. So I'm going to print child and path. All right. Let's see. What do we have? A child and path. Let's focus on IBM. IBM. Where's IBM? We have IBO. Huh. What is this? Why will we have IBO? We'll have the path. Wait, what is this path? This path goes to IBO, goes to IBM, and a child. What is the word? What is the word? I'm kind of just trying to decipher this whole thing. The word is IBM. The child is IBO. And the path, how is this possible? I already said it. All right. Get it. This doesn't make any sense. The word is the parent, right? So the word, the parent is IBM. Child is IBO. The path is this, but I have a condition that's path. Oh, path minus 2. Path minus 2. Because I cannot do path minus 1. Path minus 1 is the parent itself. So path minus, I might run into some issue path minus 2, but we're gonna take our chances. All right, we significantly reduced the number of repeats, but we still have tons of repeats. Okay, so let's see. Did we get the answer though? Hold on, I have a piece of tofu on the table. Oh, more than tofu, I have some, is that green pepper? Some green pepper and tofu. Nice. All right. Wait, did we even get the answer? We have set caught con, and this is right. Set get g gte ats its ito ibo. Yeah, we got 2. Set cat can in ins its ito ibo im is okay. We got all 3, and then we have 2 that is wrong. Set caught dot dawn con. Wait, why are they wrong? Length. Check the length. 1, 2, 3. Ah, this is so difficult to read. Stupidity. Don't do it this way. This is a different. We're gonna do print answer. And for A in ends, print and sort it. So we have a good order, print A. We'll do the same thing for the other one. So this just give us a a better idea of where we got wrong. So res, this is going to be res, and this is going to be r, this is going to be r. There we go. Yep, that's the length. That's the length. Okay, we might get it. All right. I'm gonna get a bit excited. So what we do is we're gonna get the main length is gonna equal to len res 0. If we have, right, if not res, I mean, what if we, oh, the queue will end. So if not res, we're gonna return this. And then we're gonna get a main length, and this one gonna be main length, right? And pp gonna do this, and has to say if, right, if len pp plus j, no, it's not plus j. What do we plus? Plus, no, if len pp equals main length minus j. So j, no, hold on. No, if len pp equals j, because j 0, 1, 2. So yeah, if that equals j, then we do this. And we have indent issue. Unexpected indent. What? What did we do? For this, if this equals this, then unexpected indent. Oh, yeah, it is unexpected indent. Hey, wait, what? If len p equal to j. I don't understand. I got a syntax error. That was 4. 1, 2, 3, 4. 1, 2, 3, 4. What's the problem? Line 56. Indentation error. Expected an indented block. Is it not an indented block? I don't understand. But we passed. Oh, no. We passed this test case. We didn't pass everything yet. We did not pass everything yet. Okay, so we have to go back. Oh, now this solution looks very, very convoluted. Oh my god. And I betcha if we pass and we check the correct answer, it's going to be very simple. Very, very simple. But anyway, we check this. Now we have all 3. All right, we have all 3. And submit. Pending. Judging. Ugh. I got something even worse. We got a wrong answer. Wait, let's see. How many did we pass this time? 30! We got 30 out of 32. Man. What is... Oh. This is the last name. I saw Nuth. Alright, so what is the problem? Output. Expected. I don't even know. Alright, so this is my answer. Let's just do it this way. All right, this is my answer, and this is the correct answer. All right, show me. I need to make it bigger. Okay, this is the correct answer, and that's the second level, third, fourth, fifth, the 5. My God. Matia. I think we got all the first two got right, and we have Marta and Marti. So Marta and Marti is right, and Maris and Marx, Maris and Marx, Maris and Paris, Maris and Paris, Marta and Marti. Which one? We miss Marta and Marti. We have 2 Marta and Marti. Oh, there are 3 Marta and Marti. Marta Marti. I have a party. We don't have party. We have these. Parks, Mary, Mary and Parks. But we don't have party. Why is that? Marty. So, and Marty. Alright, let's clear out the clutter. It's too many things. Martis is right, so we don't have to worry about Martis. So let's get rid of not Martis, Maris. Maris, right? No Maris. So Marta, Mari, Mary, but we don't have party. Because at the end we have Pearl, Perry, and Mary, right? Parry and Mary. So it means we want to go to see. Party should be having a. I don't know. I have hope, so we're gonna keep pushing. We feel like we're almost there, but we're not. Still need work. Still need work. So first of all, we're gonna change all this, and we need to also put this one here. This one here. All right, and then put the answer here. And last thing, put this one. That should be it. Oh wait, I have to also have a parentheses. So come out all 3. Run it. Yeah, we're missing something. Okay. That's fine. Let's first take a look at the rest. So what we have in the rest initially. Oh, I actually have quite a lot. Let's say for R in rest print. Alright, so we have, now I have 2, alright? And then I say for I in range, so go for each one. And for J, for this one, going back. So party is supposed to be, yeah, I don't have party. So, which means could be Perry, right? So when we look at Perry and we look at potential paths to get Perry, I shall get party, okay? Which means I don't have Perry. Oh my god. Oh my god, I know. So all I have is I'm basing on these two, right? So I'm based on these two, so I have Perry, which from Perry I get Parry, right? And I got Perry, Mary, something, blah blah blah. That's Perry. But after I added this, oh my god, this is not happening. Okay, okay, calm down, calm down. What do we want to do now? So basically, we want to use the trick to iterate every single one. Because if we iterate them as we push to it, it will keep going. So for R in res, all right, for R in res, J equals this. For PP to get R, this is going to be R. And after I append, it goes back to the end of res, so I'll take it out again because this one is an iterator. So this side serves as a queue. We just keep going and we keep adding more to it. And I'll get the new one pushed in, I'll get the new one out. But then I'll have repeats. This one will have repeats. We have a list out of range. No, this one I think I'll have repeats. Yeah, it's infinite loop. No, it's infinite loop. Because we are constantly adding new things. No. So we have a new result. We need to put the new result somewhere else. Yeah, we have a new result. So what? We have the new result. What if I get this and then I look for every single one, right? And we get a potential path. And from the potential path, I add to the new one. We add to it, then we how do we reconstruct the path? We got a new path coming in, right? We have a new path coming in, and we shall start from the new path. I think I have an idea. So instead of going through res, right? Instead of going through res, we're gonna go through. Now we have to go through res, but instead of going through this, right, we have to go through another one. So we're gonna have to go through the how should I say this? Like if it's the original res, we go from the main length minus 2. If it's a newly added, we need to go through a different thing, right? We're gonna go through a different thing. So we're gonna have the check start gonna equal to, right? It's gonna equal to main length minus 2, right? Main length minus 2 times len res. That's a check start. So for r in res, for j in range, this has to be, oh shoot. I think it should work. If I do enumerate, right? Then we get the index. And then we can use check start to give me the index for the starting check position. I'm going to pass in I, right? So that's that. We check from here. And res gonna append everything, but the check start gonna append something else. Gonna append j, because we are at j, and I will pass in something in front of j. So j minus 1, that's where we should start checking. So if we do this, and we run, then we pass. Look at that. We pass this, and we pass everything. Granted, it's quite slow, but all right, let's do this one more time. It's like this is the third time we submit it, right? 3 times the charm. We add another logic. Let's just run it again. No, don't run this one. You know this one pass. Let's run this one. I know this one passed. Just want to see. Oi. Try again. Pending. I think this one is good. Actually, I don't know if this one is good. Alright, let's just go for it. Submit. Pending. Judging. There we go. 1 hour and 32 minutes. We handled this not like a boss, but with very convoluted logic. Oh my god, look at this. I mean, how should I put it? The graph part is fine. Building a graph, that's okay. BFS is almost okay, but we start to have some logic here that's a little bit tough to handle. In fact, I'm pretty sure that no. The Q set is the current level, right? And if it's not in Q set, I mean it's in visited, but it's not in Q set. So that's if it's in Q set, we don't do it. So what we want is a child that has been found before, but there has to be real children. So this is what we're saying is it's not on the same level and it's not a parent. And then I append the path, right? And then this is a real tough logic here. Look at this. I don't even know the runtime. Wow, imagine this, I have to write my thought. Oh my god. Oh my god. Bad. Very bad. Muy peor. Peor tiempo. 11%. 11%. 260 milliseconds. Alright, let's try to get a logic. So first, create a graph, then BFS, but we need to record. We need to record some children, right? We need to record some children, but for some children that, but for children who are not in the same level and not on the same level of the parent and not the parent of the parent, right? But for children who are not in the same level as its parent and not the parent of the parent and not the grandparent, we also record the path that leads to this children, for this child. I was going to say children, child. This is because we can have a situation, right? Situation where two paths converge, right? Converge into one that leads to the N word. In our implementation, in the generic implementation of BFS, only one such path will be handled. Thus, we need to keep a record of the existence of the other path such that once the correct path is found, we can backtrack the correct path and see if any additional path can lead to one of the nodes in the correct path, right? Finally, we reconstruct all the paths based on the unique and separate, based on the completely separate paths that lead to and word. For each such separate path, we backtrack and add any paths that have diverged somewhere, and any path that has diverged in the past, right? Has diverged somewhere upstream, right? Any path that have diverged somewhere upstream. Now the important trick here is to also backtrack the newly added diverged path. Yeah. I know that this doesn't make any sense. I know this doesn't make any sense. So we will just have to read the code and understand there. All right, this doesn't make any sense. So, but we can write comment here. So check start. The starting point in a correct path where we shall start backtrack. Note that for a newly added path, we do not start from the end, but from where the newly addition ends. Newly addition ends. And everything else is pretty straightforward. Like I know what this is doing because we need to backtracking, and the only thing is this check start. So we're gonna say this add the starting position, backtrack start, the backtrack starting position for the newly added path. Alrighty, that's what I want to do, just like that. It's really hard for me to express myself. This is very complicated. But anyway, runtime, I have no idea. I mean, on for this, right? On for this. I shouldn't say on for this because we also have these parts. These will take time. And this thing is just gigantic blob of I don't even know what. I don't know. I don't know. I don't know the big O for this. Too complicated. But I know the runtime we get is 260 millisecond and then 11%, ranking, which is bad because the correct answer give us 50. I got 260, so it's 5 times faster. But hey, that's fine. It's a difficult question. I give myself some slack. All right, let's take a look. Hey, I think this is a record. It's the 3rd difficult question in a row that we solved on our own. Granted, it takes a long time, but it's good. Ah, thank you. Gracias, Miguel.
I want. No.
Sí.
I want to.
Sí, sí. Muy bien, muy bien. Hablas chino muy bien. Muy bueno. All right. This is an extension of word ladder. So what does word ladder ask for? I forgot. It just asks for printing out. Oh. The word ladder, that the one that the Google interview gave us, is only asking for the minimum length of the ladder, and that's like a first level. It's already a difficult question, but that's a first level. And what we have right now is a second level, which is asking not only the shortest the length, but they want you to list all such ladders. That's much harder because the previous one you do a BFS and boom, that's it. BFS, we're done. But this one we need to backtrack. All right. Also, it tells you the runtime k². I just see how long is the code. Oh Lord, it is long. Oh my God. Bidirectional breadth first search and backtracking. Oof. Coding starting consistent. Oh. All right, let's just calm down and read. Here we need to find all the transformations that exist between this and this. The minimum length, number of words. So transformation is tricky because the number of transformations may be enormous. Correct correlate with a graph, yes. That's what we know. All the direct connections of a particular word. Find adjacent words. It take ONK, yes. Now the words only consist of lowercase and letters, hence we can change each character of the word to all other English lowercase characters and check whether or not that word exists in the word list. This way the number of operations will be 25 times k², hence the time complexity will be OK². Let's read it again. K is the number of words given, and K is the maximum length of word. The words only consist of English letters, hence we can change each character of a word to all other English lowercase character and check whether or not that word exists in the word list. This particular check takes O1 and take OK in Java. The number of operations. The time. I don't understand. What do you mean? Change each character to all other English characters and check. Oh, so we make the input the dictionary in a word list into a dictionary, into a set, and for each word we're going to change for each character we change 25 times, right? So this one 25 times and see if it's in it, and then for the next one we change that, and go to the next one we change that. Okay, so for each character we change, right? For each character we change to 25 other characters and see if it's in it. If it's in it, then we're good. If it's not in it, we keep going. So take 25 times k for each word, and we still need to check for every I don't understand. You still have to check n word, right? Oh wait, we don't have to because we change every single word. Each character of the word to all other English lowercase characters and check whether or not that word exists. But we find all the words that are directly connected. I need to understand this one again. Change each character of the word. We have lots of characters. So the first character we change and we say, okay, it's inside. Now what? We're given a word, right? And if it's not inside, we keep going. Change, change, change. Boom. See that? And then change, change, change. It's good. Pass in it. And then we set the first one, and then the second one, we start changing. Oh, okay. I think I know what they're trying to do. Yeah, we find the first one. When we find the second one, then these two are connected, right? Find the third one, then they're all connected. They're all connected. I find that one hard to follow. So I'm going to just take a look. Shortest path. I have a map, a JSON list, okay. So find neighbors, string word, order set. size char. Replace the ith character with all the letters from A to Z except the original. Skip is the same. And neighbors dot pushback word. Find neighbors. Have a word. Every character in the word, and we swap. Now this is clearer. Now this is clearer. Now this is clearer. And then set, this one is a set, so we're gonna count, right? Okay. So 25 times word I, so I swap it into a C, but this only works for C++, right? Because C++, a string is not immutable. That's fine. All right, so if we can change at each position, and then we go back to the original. Yep, I got it. Okay, so now I got it. So the first part done. Now we can find all the words that are directly connected, blah, blah, blah. Now able to do this is use backtracking. All the adjacent words until we reach. When we reach, we'll compare the path lengths and find all the paths that have the minimum path length. Extremely inefficient because the number of paths between two vertices can be enormous. We need to reduce the number of traversed paths. Say the number of shortest paths that exist between is x. The number of paths that we must traverse to find the shortest path is y. The closer the value of y gets to the value of x, the more efficient our approach would be. Shows the graph that represents the connectivity among words as shown in the diagram. We want to go from red to tax, right? While backtracking on this graph, we'll also cover the edges upwards, that is from tad to ted, similar from text. We'll have the traverse to ted and rex. The key observation here is that going back in the upward direction will never lead us to the shortest path. We should always traverse the edges, the direction of begin word to end word. Never traverse up the ladder. Let's use the directed edge. Ooh, directed edge. Doesn't matter. We did that. Okay, so it's a DAG. Now for the easy part, think of the previous graph, layers. We'll build our DAG using BFS. We'll then add all the directed edges from the words present in the current layer. And once all words in this layer have been traversed, we will remove them from the word list. This way we'll avoid adding any edges that points back to the beginning word. Okay. After constructing the graph, we can use same backtracking approach to find the shortest path between beginning and end. Also know that in a graph, all paths between beginning and end obtained through BFS will be the shortest possible. Direct in direction R. Furthermore, there will not be any edge between the words that are on the same level. Therefore, iterating over any edge is one step closer. Thus, there is no need to compare the length. I don't understand. Are you saying that you're building a BFS, you're using BFS to build a DAG, and then you do DFS on the DAG? I think that's what they're saying. and we make sure we go layer by layer. Hold on. And how do we eliminate the path that does not lead to the end word? Okay, I'll read again. Once we reach a particular layer, we don't want the future word to come back to this layer. Compute our DAG. Okay, we'll then add all the directed edges from the words present to the current layer. Once all the words in this layer have been traversed, we'll remove them from the word list. This way, we'll avoid adding any edges that point towards begin word. Hold on. So from this, and we go the next layer, right? And then what? From next layer, we go to the next layer. And from this layer, we go to the next layer. And we're making sure that we keep going, and so build two graphs. The first one we build is a fully connected graph. And from that graph, we go BFS. Right? We go BFS so that we can find all the layers and we reach the end. Right? We find all the layers, and with all the layers, we also create new directions. And then we use DFS to get the results. Holy guacamole! I think I got it. Okay, store the words present in another list. Perform BFS, add the edges to the adjacent list. Also, once a level is finished, remove the visit words from the word list. Start from begin word, and while keep track of the current path. Okay. So this is find neighbors. Backtrack. BFS. BFS is to find neighbors. Find neighbors. I don't think in Python this will be fast though, because string is immutable. But still, so I think what it's trying to say is start from the beginning, right? And we find its neighbor. And once we find its neighbor, right, we add that to the graph. And then we go to the next layer, find neighbor. And when we find neighbor, every time we find it, we remove it from the word list, so we have less chance of finding it. But let's just go ONK for this, right? And eventually we'll build a graph. So after we build a graph, then we backtrack. Oof. Very good. Very good. Number of words. K is the maximum length of a word. Possible paths. In BFS, every word will be traversed once. Yeah. We'll find the neighbors using the function. Time complexity, well, ours will be nk. The total will be onk squared. Each word will be enqueued and will be removed exactly once. Yeah, that's true. Backtracking, be finding all the paths. thus the complexity will be equal to O. Oh, and also the length of the path. Yeah, that would be it. Okay, what's a bidirectional breadth search? It's better optimized. Start from begin with. Oh, we go both sides. Oh, oof. However, now we will start from begin and from end, starting backward here, and explore towards the middle of the ladder. We'll connect the words to the neighbors, which you will find using this. At each iteration, we'll have two options, either to connect edges using the forward queue or by using the backward queue. The optimal choice is to use the queue that contains fewer words. In this solution, for scenario, we'll swap. Whenever forward queue is larger, always choose the forward queue. We'll traverse the forward queue, find the neighbors of each word present using this, and add the edges. So this will also store the next layer words in visited list. Once the level is finished, we can assign forward queue. Visited, we'll repeat this process until either the size of forward queue becomes 0, sometimes there's no valid sequence, or into the contents of forward queue overlap. Forward queue or backward queue overlap. But because after completing this level, it is guaranteed that the begin and end will be connected by at least one sequence. I am going to implement solution 1. It's going both directions is the same, but no, yeah. At this point, we've got 2 hours in. The brain's a little bit tired, so let's just go with the the BFS. Oh my god, that was fast. Where one step is changing some letters. Word. Create a graph of connection G. Run BFS on this graph. All possible solutions. Steps and more details. To create a graph, create patterns. Iterate patterns and connect words. We need to run BFS. Also need to give an answer all possible. So we need to modify all of them. We keep 2 dictionaries, depth of each word, and a path to keep all possible paths. When we extract elements from Q, look at this neighbors. New element to Q there. We need to update. No, I don't like. I want to go with the official solution as well because I didn't understand. Just by a quick read. Modify. We keep 2 dictionaries. Depth of each word and path. Keep all possible paths. We extract element from Q and look at its neighbors. Add new element to Q if depth neighbors equals -1. I think I know what it's trying to do. It's trying to do this thing. It's trying to do this thing. If you keep a depth, then you know, right? Which means we add new element if it's a child. That is a directed graph. All right, hold on. Let me put my screen back. Okay. Let's code it the way I think will work, which is the official solution. So let's do the official solution. All right, so this is official solution. The idea is to first create a DAG using a DAG that leads to ANT using BFS, then use DFS to traverse the DAG and find all possible paths. Okay, so here's the deal. We need to use, this is how I use, right, to find, which is fine. So we can say DAG is going to be the default dict list, right? So we have a queue is going to be, or don't worry about a path. So queue is just going to be the word. So begin word and visited. Is everyone going to go once? Visited equals set and words is going to be a set word list. Okay, so here's where we're going to go. While queue temp equals this for word, for w in queue, right? Now, this is what we need to do. We need to traverse through words, right, and find all the words that is a neighbor, right? And then after that, we need to remove it from words. Can we do that? That'll be difficult, right? That'll be difficult. So, if we swap, right? That's when we need to swap. I see. Let's try it. I mean, it's gonna be the same runtime, so I don't think it's gonna find neighbor. Yeah, I like this find neighbor. I like this this way of saying. So we have the parent. Oh, it's neighbor. It's not this kind of word, and words. Words are going to be a set of this. Word is just going to be an str. I don't even have set. Set. All right, and what are we going to return? We're going to return the neighbor, right? We're going to return the neighbor. So for the word, right, and we're going to return a list of neighbors. Yeah, we're going to return a list of neighbors. And we are changing words as well. Hold on. Find neighbors, right? So we're going to find neighbors, which is going to be a list of neighbor. And is that what we want? That is what we want. So I'd say find neighbors. And I'm going to return a list of neighbors, right? And I'm going to say we have a word, right? Word list equals list word. Right? I'm going to say for each position, right? For each position, for I in range, len, word, old equals word I, right? And then rest equals this for letter in what? In range 26, so I have 26 letters, right? For J, let's call it J, right? So new equals char. I think it's 97, right? It's 97. ASCII table. I think is 97, yeah. So char 97 plus J, new, and if new is not equal to old, and dot join, hold on, not equal to old, right? So we're gonna say word list I equals to new, and if dot join word list is in words, right? And rest dot append. Oh, I don't like it. I don't like it. For I in line word, old is going to be this. For J in 26, new is equal to this. And if that's fine. We don't have to even to do this, right? We'll just say new will equal to word plus, so to I, right? And shouldn't be I plus 1. For changing, right? So for I, so that's gonna be an empty, and I plus 1 here plus word I plus 1, right? So that's changing the first. So new equals this, and we say if new is not equal to word and new in words, then we say rest dot append new, and that's the key, words dot remove new, right? So we go through 26, we go to the next one, right? And then go to the next one, and we go and then return rest, and words has been updated. So for W we have neighbors equals self dot find neighbors, find neighbors W and words. Let's call it word set so we know what we're dealing with. It's going to be word set. Hold on. I got it wrong. Words set. So now we got the neighbors, right? Once we get the neighbors, the neighbors needs to be in a queue. Right? The neighbors needs to be in a queue, and it has to be visited as well. And of course, this one has to be a begin word here. Yeah, for W in Q, we get all the neighbors, right? And I'm gonna say for neighbors in this, there's a neighbors, and temp dot append neighbor, right? Well, it depends if neighbor is not in visited. Will neighbor being visited? I don't think neighbor will be in there because we are removing from word list. So I think that's temp. I need to build up the DAG. So I think that's the temp. Right? I think I just say temp.extend this every time. What does extend do? I forgot. Did we return a new thing or a.extend b? Yeah, just add it. So temp.extend, that's the new neighbors. And when we do this, we'll also remove the words, right? So for each W in Q, we get the new children. And hold on, this is not right. So I have to say neighbors equals to this because we need to handle the neighbors as well. Nah, I don't like it. For neighbor in this, temp gonna append the neighbor, and DAG w.append neighbor, right? So the neighbor, blah blah blah, we're done, and so neighbor, and then we also need to check if the neighbor is for W in Q, right? For W in Q, this one will be done. And because we're removing words, there will be fewer and fewer every time, which means we don't need visited actually, I think. So Q equals temp, right? So we'll go back, and whenever W is if W is AND word, then if W is AND word, then we break. What do we say? If W is the AND word, then we got it, right? Then we got it. And append neighbor. W already, the AND word already appended. So once this one comes out, we don't have to go anymore. So we just say break, right? We break it. But what if we have something else? Then the temp is already in. So no, we're gonna say Q equals to this, then break. So we just basically we break it out. Oh, I cannot do that. Cannot do that. If the current word is the AND word, which means on this level we have this one out, and that shall be the end. That shall be the end. That shall be the end. So we're gonna break, right? We're gonna break, and if we break, we're gonna have an else, right? If we break it, so else we say break, right? We break it, right? Okay. That word let's do this. Let's do dag w equals dag w. We want a signal if w is inside, right? So I say dag w equals empty string. And then when we come out, we say if an word is not in dag, right? Then we return edge case. Now we have the dag. Now we're going to do is check if it works. So we're gonna print dag, right? Return this, and we use the simplest check. This is the check. Solution 2. What happened? Solution 2, I didn't print out dag. Alright, well, something is wrong. Well, Q, let's print dag here. Oh. This does not work. And now I go through, I think I remove everything from neighbors. What? W for W in Q. W is begin word. It's not. So neighbor in this. Let's print neighbor. What do we have in neighbor? We have hot, right? We check. We got hot. So we got neighbor and words set. Okay. Temp.append dag w.append neighbor. Want to get out. Yeah. It shouldn't trigger else. Oh. Yeah, it does trigger else. So nope. Tag w dot append empty, right? So when we break out, I want to check if w in dag, then break, right? And now we can print dag. It's still not right. Not w in dag. It's n word in dag. Okay, so hit the hot dot a lot. Let's go check. Hot dot a lot dot to dog. Lot to log, dog to cog. And how about log? Log need to go to a cog as well. We have an issue. We have an issue. Hold on, let me think. What is going wrong? I don't think we should remove here. So let's not remove here. If we don't remove here, this is just for each word in the, we shouldn't remove here. We remove here, right? Which means for neighbors, we do this, dag is equals to this, and then after we've done all the neighbors, then we remove it. So I think we do need neighbors equals this, right? And for neighbors in neighbors. I don't have to. We can just say, hold on. We can just say temp dot extend neighbors dag w dot extend neighbors and word set equal minus equal to set neighbors. All right, try this. Now hit hot dot lot dot to dog lot to log dog to cog. Hey, what is still not? A log does not go to. Wait, what? Oh, I think this has to be removed at the end. Right? Has to be removed at the end. So at each level, I get all remaining. And so what we're gonna do is temp is the next queue, right? Temp is the next queue. So shouldn't we just remove? Hold on. So I'm looking at W current word, and I'll find all my neighbors. Right? All my neighbors. And we find all my neighbors, and then the next one we find all my neighbors, which is fine. But when I find my neighbors, the neighbor cannot be on the same level, right? Hold on, let me think. The current word, right? And I find all my neighbors. Okay, I find all my neighbors, and after that, I cannot remove all my neighbors. No, you cannot, because that one might have the same thing. So I got all my neighbors, and temp.extend all the neighbors. That's the next level, right? That's the next level. And we don't remove words set, and I will go to the next one, right? All my neighbors. And I'll go to the next one. And the next one cannot be invisited. Right? Cannot be visited. If it's visited, then I might need to use visited. But it's not. Wait, how do we do this? It's W in the queue, right? And then for each word, we're gonna have neighbors. We find all of its neighbors. And then, after we find these neighbors, we cannot remove them because someone else might find the same neighbors. We only remove after the entire level is done. Right? After the entire level is done. So now we have the second one coming out, and we do whatever we need to do. Third one coming out, we do whatever we need to do. And then once we're done, those are the neighbors. Right? Those are the neighbors. Those are the neighbors of all of them. And then the tag is fine. Right? The tag is fine. This part is fine. because this one records the edges. This needs to be slightly different, right? And then that's all the next level, right? All the next level, which means the word set we need to remove the next level. Hold on. So neighbor is fine. What if we use this as also a set, right? We do this as a set, and we say temp plus equal to a set neighbors. Dag, not dog. Dag can extend the. I think I should return a set. We can return a set. Why don't we make everything a set? See if we make everything a set. This is going to be a set. Q is actually a set. Everything is a set. Temp is a set for everything in it. And this one, rest is going to be a set. And this is going to be add, right? Now return rest. So this is going to be a set. Neighbor is a set. So we can directly just plus this. And this one is going to be plus equal to this, right? Once we're done, it's going to be minus 10. Right, we remove the entire next level. Right, we remove the entire next level. So, word set we need to remove. Word set that remove begin word as well. Oh, but it says begin word is not in it, right? I think it says begin word is not in it. Does not need to be. Yeah, but we need to remove begin word if begin word is in, right? So if begin word in word set, then word set I'm going to remove. Begin word. Now Q temp, and we do this. Let's see. Temp plus neighbors, right? Dag plus equal neighbors, and then we remove all the temp. Doesn't apply to str object. Where? Rest.add new. Huh? Oh, shoot. Unsupported object. I thought we can do this. I think it's temp.union. Wait, union new set object. So I think it is temp.union. This is gonna be w.union, and this probably we don't have. Do we have this? Oh, we have an append. Where? Oh, this one. Add. Yep. Right. Okay, we can do minus, so we cannot do plus. So hit hot log dot cog. Now we have cog, right? So now, so this is building the DAG. Right. Say build DAG using BFS, and this is traverse the DAG. Traverse DAG using DFS. Okay, so what we're gonna do, we're gonna say everything that reaches the end will be correct. So def DFS would probably need a path, right? So would is going to be str, path is going to be a list of str, and this one to return none. We're gonna also do res equals this, right? So DFS if word is equal to n word, then res dot append path. Copy it, right? And then else for each word, then we're gonna say for neighbor in DAG word, right? For neighbor in DAG word, DFS neighbor path plus neighbor. No, path plus word. Hey, wait, hold on. Path plus neighbor. Path plus neighbor. Path plus neighbor. All right. And then return res. I mean, this is not really backtracking because we set the path. We don't really change path. And we can change path. Or fail because we didn't get anything. Because we didn't call it. DFS begin word path we say is empty. No, path has to have begin word in it, right? Okay, so this one pass. Okay, try this one, pass. This one pass. They all pass. Visited, but not used. So I don't need visited because I'm deleting, right? If I'm deleting, then I don't need to use. Okay. Build a DAG. All right, try this. Submit. We got 60 milliseconds. I think that's the official. Yep. So the difficult part is to build a DAG. The DFS is very simple. Right? The DFS part is very simple. It's not difficult at all. The difficult part is to build a DAG. I think the ideal is we need to remove things. Right? That's the thing. And we can use set for everything to make things easier. All right, temp and a union. Temp is the next. What should I say? Temp is the next level, right? And that's the neighbors. And also, of course, right, we're in a union, but we do not remove the word set yet. Because everything we have to keep the word set intact, so everything can get all the possible neighbors. Right? Every one at the current level get all possible neighbors going down, right? Going down. And once we do that, then we remove everything. That's the next level. We remove everything, and then we go to the next level, right? Then we make sure that we're always pointing down, right? Always pointing down. This is the key step to make sure we do not point backwards. And we're using set just to make everything easier. Good solution. So this one is O. This we have to go through every word. So ON, and each time, right? To build a DAG, and we have this part, and this is K. So this one is OK squared. Right? This one OK squared, where K is the length of word. Right? This is OK squared because of this part is OK, right? OK squared. So, no, really? Yeah, 25. It's actually, so 25. And I said 26 in this case. Right, because 26 times, each time is K. And then there's 26K squared. And I'm coming here, right, while Q. And this is every single word is once, right? We hit every node once. And for every one, we need to call neighbors. Call neighbors. Neighbors. We call neighbors. What's the runtime? This one, it says 26K squared. That's actually not right, because I go with every one and I check. That's 01, right? So new is not equal to this. I add it. That's 01. And that could be ON, right? Neighbors can be N. Or maybe not. How many neighbors? Well, if we got all the neighbors, then this, yeah, I think that's ON K squared. Yeah, ON K squared plus M, right? Where N is the length of word list, K is the length of word, beginning word, each word, and M is the number of paths. All right, so this one runs at 60 milliseconds. That's 60 milliseconds. 54% ranking. All right, that's it. Wow, the actual solution is much shorter, right, than the one that I wrote. This is an important thing that we can learn, right? Build a DAG instead of a fully connected graph. Or build a DAG, and because the DAG allows you to restrict what the paths can be. All we need is from the beginning to the end, flowing in one direction, right? And we use BFS to create each layer, right? And then once we reach the end word, we know that is the shortest path. And we include all the neighbors, all possible nodes in it. And they all connected one direction from begin to end. And then the actual picking of the path, we don't have to think about it at all. We just write a DFS. And the DFS is very simple to write. It's a good question, very good question. And it tests, let me put that as a good, I'm going to add to a good interview question. It's difficult, but I think in the actual interview, if the interviewer is good, he shall be able to guide the interviewee. Like, okay, think about it, right? We want to find the shortest path. So what type of, well, of course, first we need to get the candidate to know this is a graph, right? And after the candidate knows it's a graph, the candidate shall be able to figure out, okay, we probably need to use BFS to get the shortest path. And then when he starts working on it, he'll be like, okay, if we go BFS, how do I collect all the paths? And that's when the interviewer can suggest, all right, how about we do a DAG first, all right? And then if we have the DAG, then the paths will be trivial to find. That's something to think about. All right, that'll be it. I'll see you guys tomorrow. Adios.